Hello, students, and welcome. So, are you ready for an absolutely amazing journey today? We're going to figure out how the simple English words that we type into a computer can magically turn into action. It's a journey from our code all the way down to the electric current that's zipping around inside the machine. So, let's get started.
All right, let's start with a really strange question. How do we make a rock think? I know, it sounds a little crazy, right? But think about it. What is a computer processor, really? It's made from sand, silicon. We've somehow managed to teach a lifeless object to think. But how? Well, that's the mystery we are going to solve today.
So, the very first, and honestly the biggest, challenge here is communication. You see, we humans and computers, we just don't speak the same language. Not at all. There's this massive gap between our complex thoughts and the machine's super simple operations.
In this right here, this is the heart of the problem. We think in terms of play this song or add these two numbers. But a computer, at its most basic fundamental level, only understands two things. Is there current in the circuit or not? Is the power on or is it off? And we represent this with a 1 for on and a 0 for off. That's it. That is binary, the only language a computer truly understands.
So, to build a bridge across this huge communication gap, we invented something brilliant: programming languages. They act like these amazing translators that connect our human intentions to the machine's world of ones and zeros.
So, in simple words, what is a programming language? Well, just think of it as a set of rules and instructions that tells a computer exactly what to do. Just like we use Hindi or English to talk to each other, we use languages like Python or C++ to talk to a computer. Now, these languages mainly fall into two categories: high level and low level. And listen, high or low doesn't mean one is better or worse. It's all about the level of abstraction, which basically means how far away or how close we are to the actual hardware. A high-level language is more like English, so it's easy for us humans. A low-level language, on the other hand, is much, much closer to the machine's hardware.
You've definitely heard of these high-level languages. I'm talking about C, C++, Java, and of course, everyone's favorite these days, Python. Their biggest advantage is that they are machine-independent. What does that mean? Well, it means the code you write on one computer can often run on totally different kinds of machines without too many changes.
Okay, now let's talk about the low-level guys. Right at the very bottom, we have machine language. This is pure zeros and ones, the stuff the computer understands directly, no translation needed. Just one tiny step above that is assembly language. Instead of just numbers, it uses short, easy-to-remember codes called mnemonics, like add for addition. To turn this into machine language, it needs a special translator called an assembler.
Okay, so we've written our code, let's say in Python. Awesome. But now, how does it actually get turned into the zeros and ones that the computer can understand? This is where our translators enter the picture.
All right, pay close attention because this is a classic exam question. What's the difference between a compiler and an interpreter? Let's use an analogy. Imagine a compiler is like a translator who takes your entire book, translates the whole thing at once, and then gives you a brand new translated version. That's why its final execution is super fast. On the other hand, an interpreter is like a live translator at a conference. They listen to you speak, one sentence at a time, and translate it on the spot. So it reads, translates, and runs your code line by line. And this process is, naturally, a little slower.
Okay, so up until now, we've been in the world of software, the world of code. Now we're going to take a deep dive into the hardware. How do these zeros and ones actually physically get things done inside the machine? So the big question is this. We have the zeros and ones, we get that, but how does a physical machine actually process them to make a decision? How does it decide to play a song versus doing a calculation?
The answer is logic gates. These are the absolute fundamental building blocks, tiny, tiny little switches that every single digital circuit is made of. Your phone, your laptop, even a supercomputer, it's all built from these. And each tiny gate makes one simple, logical decision. And by combining these super simple gates over and over again, we can perform an almost infinite number of complex operations. So, let's meet some of the most important ones, the basic gates and, of course, the universal gates. First up, we have the AND gate. Its rule is very simple and very strict. I need everything. The output will be 1 or on only if both of its inputs, A and B, are 1. If even one of those inputs is 0, the output is 0. Done. It's kind of like needing a ticket and an ID to get into a concert. You have to have both.
Next, we have the OR gate. Now this one is much more relaxed. Its rule is either one is fine. The output will be 1 if either input A or input B is 1. The only way to get a 0 out of this gate is if both inputs are 0. It's like paying for a bus ride. You can use a bus pass or cash. Either one will work just fine.
And here is the simplest gate of all, the NOT gate. It has just one job. Whatever you give it, it flips it. It inverts the input. Give it a 1 and it'll give you a 0. Give it a 0, it'll give you a 1. That's it. That's all it does.
Now, on to the universal gates, NAND and NOR. These are really special. Why? Because you can build any other gate, and, or even not, using only NAND gates, or only NOR gates. This makes designing circuits incredibly efficient.
So let's compare AND and NAND. The name tells you everything you need to know. NAND is just not AND. It's basically the complete opposite of an AND gate. So if you take the output of an AND gate and run it through a NOT gate, you get a NAND. See that little circle on the symbol? That little bubble means not. And you can see it right there in the truth tables. They are the exact opposites of each other. And it's the exact same logic for OR and NOR gates. NOR simply means not OR. It's the total opposite of the OR gate. And again, you've got that little circle on the symbol, and its truth table is the complete inverse of the OR gates table.
And there you have it, the complete picture. I mean, think about it. We started with a single line of Python. A compiler or an interpreter translated that into machine code, into zeros and ones. And then, deep inside your computer's processor, billions of these tiny logic gates use those signals to make a decision and show you a result on the screen. The journey from a simple idea to an actual electrical current, it's pretty incredible, isn't it?
So, after all of this, here's a final thought for you. Today's incredibly complex artificial intelligence, it's all built on these simple, logical rules of on and off, 1 or 0. It really makes you wonder, right? What will be the next fundamental building block of intelligence? अगर आपको ये वीडियो हेल्पफुल लगा हो, तो प्लीज़ लाइक, शेयर और चैनल को सब्सक्राइब करना मत भूलना। सारे PDFs के लिए मेरा टेलीग्राम चैनल ज्वाइन करें, लिंक डिस्क्रिप्शन में है। Keep watching and stay tuned.